Okay, in this video, we going to describe topology on the Cartesian product of two topological spaces. For example, let's say X is a topological space and Y is a topological space. So in this video, we're going to study the topology on the Cartesian product of X and Y. And that topology is called product topology on this Cartesian product of two topological spaces X and Y. We will give a formal definition of topological space in a few minutes. Uh, Before that, let me give you a lemma. This lemma will tell us what is the basis of topology on X cross Y. Okay, here is the lemma. Let's say X and Y are two topological spaces. We have given two topological spaces X and Y. Then the collection script B, which is the collection of all these Cartesian product such that U is an open set. U is an open set in X and B is an open set in Y. So here we have two topological spaces X and Y. Now we are considering this collection. The collection is the collection of Cartesian product U and B, U cross B, such that U is an open set in X and B is open set in Y. Since X and Y are topological spaces, so X cross Y is one of the element of this collection, because in order to be a member or an element of this collection, the first thing, that element has to be Cartesian product, and both first and the second set of that Cartesian product, they have to be open. First one is open in X and Y, the second one is open in Y, and obviously X cross Y is an element of this collection, because X and Y both are topological spaces, and topological spaces, they are the open set. So X is open in X and Y is open in Y. Then this collection is a basis for our topology. Is a basis for our topology on X cross Y, and that topology, or the topology generated by this basis, is called the product topology. So basically this lemma tells us, if you have a product topology on the Cartesian product of two topological spaces X and Y, then this lemma tells us what is the basis of that product topology. Okay, the proof of this lemma is easy, and let me give you the quick proof of this lemma. So basically, before we start talking about the proof, let me describe the element of this basis graphically. Okay, let's say this one is my X, topological space X, and this one is my topological space Y, and then the Cartesian product of X and Y is this whole this whole set. Now the element of this basis, they are going to be like this graphically. Let's say U is an open set, in this set X, and then let's say V is an open set in Y. Now what we do is we take the we just take the Cartesian product of U and B. When we take the Cartesian product of U and B, so we're going to get this set. So the element of, I think this should be a little further here. So the element of this basis, they look like this set here graphically. Okay, now let's prove this one. Let's prove this lemma, or let's show that this collection is a basis for our topology on X cross Y. Basically, we want to show that this collection is a basis. So we're going to use a definition of basis to prove this lemma. According to the definition of the basis, or if you want to show this collection is a basis, then there are two conditions that we need to prove. The first one is for each element in this Cartesian product, you should have an element in this collection such that that element of this Cartesian product is gonna be an element of this is going to be an element of the element of this collection, and that is obvious because we already, as I said earlier, this X cross Y is itself it's itself an element of this collection, because X and Y both are topological space, and if X and Y are topological space, X is open in X and Y is open in Y. When we take the Cartesian product of these two set, we get X cross Y, and that is and obviously that this Cartesian product is in this collection. So in order to be this Cartesian product in this collection, the first set has to be open in X and the second set is open in Y. So that's why no matter what point you pick on this Cartesian product, always you can find an element in this collection, and that element is gonna be X cross Y. So if you want to write formally, you can write down as like this: X cross Y is an element or is in this collection because X is open in X and Y is open in Y, and since this is X cross Y is an element of this collection, because X is open in X and Y is open in X, so that we can say that if you pick any element of this Cartesian product, that element it always lies in this Cartesian product, and that Cartesian product is an element of this collection. So here we just prove that if we pick any arbitrary element in the Cartesian product, for that element we can find an element from this collection such that that element of the Cartesian product is gonna be it lies in the element of this collection. That's the first condition for basis. And the second condition of basis is if there is an element in the Cartesian product which is in the intersection of two basis element, then there should be another basis element containing that point of the Cartesian product, and that third or another basis element should be inside the intersection of those two basis elements. Okay, for that one, to prove the second condition, suppose XY, this order pair, is an element of the Cartesian product such that XY is in the intersection of two basis element, let's call those basis element b1, b2, where, and we know that the element of or the basis element, they are all they are in the they are in this form. That means they are in the Cartesian product form, where let's call b1 is u1 cross b1, and b2 is u2 cross b2. So here we have assumed that xy is this x comma y is an element of this Cartesian product, and that element is in the intersection of two basis element b1 and b2, where b1 is the Cartesian product of u1 and b1, b2 is the Cartesian product of u2 and b2, where u1 and u2, they are open set in x, and b1 and b2, they are open set in y. Now, to show this collection satisfy the second property of basis, what we need to do is we should be able to show that there is a third or there is another element in this collection, or there is another basis element, such that this guy xy lies on that basis element, and that basis element is a subset of this intersection. That's what we need to show here. Okay, now I'm going to let me describe this this condition, or using graph, or let me describe this this condition using a graph. So what we have so far here is, let's say this is our y topological space, and this one is our x topological space, and this is y, and that's the Cartesian product of these two topological spaces. And now here we have a point x, y, or just let me write down this. It has the two coordinate x and y, and we are taking this point is in the intersection of b1. So b1 is u1 cross b1, and b2 is u2 cross b2. Now u1 is open set in x. Let me take this is my u1, okay, and then b1 is open set in y. So let me take this is our b1. So in this picture, my u1 cross b1 is gonna be this set. This is my u1 cross b1. So basically it is our b1. All right, now b2, let's sketch the b2. So here b2 is u2 cross b2. u2 is open set in x. So let me take that u2 is this one. This is our u2. This guy is u2, and then let me take b2, which is open set in y. So let me take that b2 is this guy. This is our b2. Okay, this is our b2, and then in this graph our u2 cross b2, which is going to be, this is going to be this set. Okay, all right, so this is our b2. The one that I mark with red is b1, and then the one I mark with green is b2. Now this point is, obviously you can see here, is in the intersection of intersection of b1 and b2. So which is this guy is intersection of b1 and b2. So this is now the point xy is in this intersection. Okay. Now here. Now you can see here, so this part, this is the intersection part of b1 and b2, and our point x1 xy is inside this intersection. Now we need to show that there exists the basis element such that the point xy is in that intersection, is in that basis element, and then that basis element is inside the intersection. Now we can take that basis element is like this intersection part here. So if you look at the graph here, the intersection part is going to be Here you can see that the intersection, which is this one. So basically intersection part is this one. That's the intersection of u1 and u2. The horizontal line here, that's gonna be the intersection of u1 and u2. So this part is our u1 intersection u2, and then now this part, which is the intersection of b1 and b2. So this one is the intersection of b1 and b2. So basically this intersection part is the Cartesian product of, so this guy is u1 intersection u2, and this guy is b1 intersection b2. So basically this the intersection part is, so intersection part here we can write down the intersection part, intersection of b1 and b2, which is the intersection of u1 cross b1, intersection u2 cross b2, and that is this intersection part, which is the Cartesian product of u1 intersection u2, u1 intersection u2 cross b1 intersection b2. Okay, b1 intersection b2. Okay, so that is the intersection of those two basis element. And obviously this Cartesian product, this Cartesian product on the right side is one of the element in our B, script B, because this guy u1 intersection u2, so u1 and u2 both are the open set in X, and in topological space intersection of two open set is open, so is open in X, is open in X, because u1 and u2 both are open in X, and then intersection is open. And similarly this guy b1 intersection b2, which is open in Y, so that this guy this Cartesian product is in script B. So finally for for this xy, which is in the intersection of b1 cross b2, sorry, intersection of b1 and b2, so we found the basis element, which is this Cartesian product. So we found that basis element, which is the Cartesian product, and obviously this guy is since this is itself the intersection, so obviously this is the subset of this intersection. So there is b3, and that guy b3 is u1 intersection u2 cross b1 intersection b2 in script B, such that xy is in b3, and b3 is subset of b1 and b2, because in fact b3 is the is this intersection. So finally this guy script B satisfy the both property, both condition for the basis, so that this guy script B is a basis for a topology on X cross Y, and that topology is called the product topology. So basically the topology generated by this basis, we have just proved that this collection is a basis. Then the topology generated by this guy, this basis, is called the product topology. Now let's formally define the product topology. Okay, so the product topology, which is the topology generated by script B, which we have defined in the basis. We have defined in our lemma. The topology generated by script B is called product topology. It's called product topology on X cross Y. Okay. Now we just formally define the product topology. So this lemma it tells us so what is the basis of a product topology on x cross y. Now I'm going to give you next lemma. So the next lemma, it tells us how to find the basis of product topology on x cross y using the topology using the basis of the topology on x and also the topology on y. So that means if you know that so we are going to find the topology we're going to find the basis of topology on x cross y. So that is basically the basis of the product topology on x cross y using the basis of topology on x and also topology on y. So I'm not going to give the proof of this lemma. If you are interested, you can take a look proof in Munker's book. Okay, now let me state this lemma here. Let's say x is a topological space and script B is a basis for a topology on X, and Y is another topological space, is a topological space, and C is a basis for a topology on Y. So we have two topological space X and Y, and script B is a basis for a topology on X, and this script C is a topology is a basis for a topology on Y. And then so this lemma, it tells us then the collection, then this collection which is script D. So you can read this one as script D. This collection, which is the collection of all the Cartesian products, such that B, the first element of the first set of this Cartesian product, this B is the is an element of script B, or B is the basis element for the topology on X, and C is the C is a basis element for the topology on Y. That means C is in script C. Then the collection, this collection is a basis for a topology on X cross Y. Basically, this collection is going to be a basis for the product topology on X cross Y. So this lemma, it tells us how to find the basis for the product topology on X cross Y using the basis for topology on X and basis for the topology on Y. So to find the basis for the product topology, basically what you do is you just take the Cartesian product of each element of the basis for a topology on X with each element of the basis for a topology on Y. So that's the statement of this lemma. Now I'm gonna give you two examples how to use this lemma to find the basis of product topology on the given Cartesian product. Example. First example. Let's say X is a set of a real number, and let's consider the standard topology, and we also call the standard topology is order topology, because we have seen that the standard topology and the order topology are the same topology on R. So consider the standard topology or order topology on R. Okay, So let's say x is this guy, and then we're gonna say the y is also the same thing. Okay, y is again the set of real number, and then let's consider this r with the standard topology or order topology on r. And now we know that the basis for the standard topology and the order topology, so the basis for the standard topology or the order topology on R, they are the collection of all the open interval of this form, such that A and B are the element of R and A is less than B. So you can say in this lemma B is this open set, and then C, if you want, is gonna be is going to be the collection of those open intervals. So maybe let me call that just to match up with this lemma. Let me call the basis for the standard topology on R. Let me write down like this: C D, such that that's A B C D. These are just the real numbers, so don't be confused with A B C D. Okay. C is less than D. Okay, now we have the topology on R, and then also we have the basis on R. Then by using this lemma, then by the above lemma, this collection, then the basis for the product topology on R cross R, basis for the product topology on R cross R is going to be the collection of those Cartesian product. You need the basis element for the topology on R, which we have taken as the open interval of AB, and you take the Cartesian product of the basis element for the topology on the second topological space R, which are again the open interval, such that A, B, C, D, these are these are the real numbers with A is less than B and C is less than D. So then this collection, or the collection of those Cartesian product of those two open set is a basis for the basis for the product topology, the basis for product topology on R cross R, which is also called the R square, is the basis for the product topology on R cross R. Then that product topology, or the topology generated by this basis, is called the standard topology, which is this topology. The topology generated by this collection is called, which is called the standard topology. The standard topology on R2. So we have already described the standard topology on R, and then the topology generated by this basis is called the standard topology on R2. So we found the basis for the product topology on R cross R. So this collection is the basis for the product topology on R cross R, and that product topology, or the topology generated by this basis, is called the standard topology on R2. So let me describe the element of this basis graphically. Let's say this is our real line, and this is another real line, and so this plane is the R cross R. Now we need those Cartesian product. Let's say this is our AB and this one is our CD. Both A and AB is the open interval. That means A is not included, B is not included, C is not included, and D is not included. So when we take the Cartesian product of those two open sets, so it's basically that's gonna be this rectangle. Okay, this rectangle without boundary. So basically it's a rectangle without the boundary, because the A and B, C and D, they are not included. So the collection of such open rectangle, they are called the open rectangle, the rectangle without boundary. The collection of such open rectangle in plane is a basis for the product topology on R2 or the standard topology on R2. Okay, now let me give you one more example. Then, okay, the next example, example number 2. Let's say X is a topological space A, and Y is another topological space. Let's call 1 and 2, and let's consider discrete topology, discrete topology, uh, consider discrete topology on each topological spaces X and Y. Now we have two topological spaces X and Y, and we are considering the discrete topology on each topological space. Now we want to find the basis element for the product topology on X cross Y. So we want to find the basis for the product topology on X cross Y. So in order to find the basis for the product topology on X cross Y, we need to find the basis for the discrete topology on this set, and also the basis for the discrete topology on Y. And we know that the if you take the 1 point subset of X, then that collection is going to be a basis, and that will generate the discrete topology. So let's say script B is a basis for the discrete topology, topology on X. Let's say script B is the basis for the discrete topology on X, and C is a basis for the discrete topology on Y. Then B is going to be the collection of all 1 point subset of X, and since X has only one element, so that is simply this set A. And then C is the collection of 1 point subset of Y, which are 1 and 2. Okay, now these are the basis. First one is the basis for the discrete topology on X, and second one is the basis for discrete topology on Y. Then according to that lemma, now the basis for the product topology on X cross Y, then the basis, let me call that as script D, is gonna be, what you do is you take the Cartesian product of each element of this B with each element of this basis C. So since script B has only one element, now we need to take the Cartesian product of this set with each element in the other basis. So it's gonna be Cartesian product of A with with the first set, and the Cartesian product of A with the second one. And then when you take the Cartesian product, that's gonna be, if you take the Cartesian product of this set with this one, is simply the order pair of A and 1, and this is the order pair of A and 2. So this is the basis for the product topology on X cross Y. So this is how we can find the basis for the product topology on the Cartesian product of given two topological space, using the basis for using their respective basis for their topology. Okay, all right. Okay, that's all for the product topology. Now so far we use the basis to describe the product topology, but sometimes it's gonna be more useful if we describe the product topology using the sub basis. So next we're going to describe the product topology using the sub basis of given topological spaces, and which is we will describe in next video.